This video is brought to you by mywayteaching.com.
In this part, let us study what is heat transfer. Okay, so we have seen that heat is energy transfer from one system to another, or from one part of the system to another part, rising due to temperature difference, isn't it? So it is just the energy transfer from one system to another, or we can say from one part of the system to another part of the system, which is mainly due to temperature difference. Then there are various ways by which this energy transfer takes place. You know, basically, there are three distinct modes in which this heat transfer takes place. That is heating by conduction, convection, and radiation, as you can see in this figure. So, this is heating by conduction, heating by convection, and heating by radiation. Okay, so now let us study the first one, that is heating by conduction. Conduction is the mechanism of transfer of heat between two adjacent parts of a body because of their temperature difference. Suppose one end of the metallic rod is put in a flame, and the other end of the rod will soon be so hot that you cannot hold it by your bare hands. You have experienced it, isn't it? So why that so? Because that heat has transferred from one end of the rod to the other hand. So here heat transfer takes place by conduction from hot end of the rod through its different parts to the other end. Gases are poor thermal conductors, while liquids have conductivities intermediate between solids and gases. So solids are very good heat conductors. Heat conduction may be described quantitatively as the time rate of heat flow in a material for a given temperature difference. We can define heat conduction as quantitatively time rate of heat flow in a material for a given temperature difference. You just consider a metallic bar of length L and uniform cross section A with its two ends which are maintained at different temperatures. This can be done, for example, by putting the ends in thermal contact with large reservoirs at temperatures say Tc and Td, as you can see in this particular example. So here we have considered a rod of length L and having the cross sectional area A, and we are maintaining the two ends of the rod at two different temperatures by putting the ends in thermal containers with large reservoirs. One is at the temperature Tc and the other one is at the temperature Td. Okay, let us assume the ideal condition that the sides of the bar are fully insulated so that no heat is exchanged between the sides and the surroundings, because here no heat exchange takes place between the surroundings and the system. After some time a steady state is reached, the temperature of the bar decreases uniformly with the distance from Tc to Td. From Tc to Td, the temperature decreases uniformly. Okay, the reservoir at sea supplies heat at a constant rate which transfers through the bar, and it is given out at the same rate to the reservoir at D. So this reservoir at C transfers the heat at a constant rate and it is given out at the same rate to the reservoir at D. And even it is found experimentally that in the steady state the rate of flow of heat uh, H is proportional to the temperature difference. Rate of flow of heat, that is nothing but H, is proportional to the temperature difference. And even it is proportional to the area of cross section A and inversely proportional to the length L. So we can write H is equal to K A temperature difference Tc minus Td and inversely proportional to the length L. So the constant of proportionality K is called as thermal conductivity of the material. Okay. The greater the value of K for a material, the more rapidly will it conduct heat. And the SI unit for this thermal conductivity is joule per second per mole per Kelvin, or in other words we can write it as W per m per Kelvin. So the thermal conductivities of various substances, it is given in this table. Okay, these values vary slightly with the temperature, but it can be considered to be constant over a normal temperature range. So here we can see for some of the metals the thermal conductivity is given for silver, copper, aluminium, brass, steel, lead, mercury. And here it is thermal conductivity for some of the non-metals, which is given for insulating brick, concrete, fat, felt, glass, ice, glass, wool, wood and water. And here it is given for some of the gases, that is air, argon and hydrogen, 0.024, 0.016 and 0.14. Compare the relatively large thermal conductivities of good thermal conductors, the metals, with relatively small conductivities of some good thermal insulators, such as wood and glass wool. Isn't it? You can see from this table they are relatively good thermal insulators. And even you may have noticed that some of the cooking pots have copper coating on the bottom. Being a good conductor of heat, copper promotes the distribution of heat over a bottom of a pot for uniform cooking, which is very much required in cooking. So only we use copper at the base. Plastic foams, on the other hand, are good insulators, mainly because they contain pockets of air. So gases are poor conductors. Low thermal conductivity of air, we already know this, isn't it? And heat retention and transfer are important in many other applications. You can see the houses which are made of concrete roofs get very hot during summer days because thermal conductivity of that concrete is not still small enough. Even though it is much smaller than the metal, but it's not that much smaller, so only we can feel that heat during the summer. And people usually prefer to give a layer of earth or foam insulation on the ceiling so that heat transfer is prohibited and it keeps the room cooler. And even in some of these situations, heat transfer is very critical. For example, in a nuclear reactor, for example, elaborate heat transfer systems need to be installed so that the enormous energy produced by nuclear fission in the core, it transits out sufficiently fast, thus preventing the core from overheating. Okay. Now let us see a very simple problem. The problem is, what is the temperature of the steel copper junction in the steady state of the system, which is shown in the figure, and they have given the length of the steel rod as 15 centimeter, length of the copper rod is 10 centimeter, temperature of the furnace is 300 degrees Celsius, and temperature of the other hand is 0 degrees Celsius. Area of cross section of the steel rod is twice that of copper rod, and thermal conductivity of steel is 50.2 and that of copper is 385. So these are the data given. You just consider this figure as they have said in question. The insulating material around the rods reduces the heat because heat loss from the sides of the rods. The insulating material which is around the rods, it reduces the heat loss from the sides of the rods. So heat flows only along the length of the rods. Okay. And consider any cross section of the rod. In the steady state, heat flowing into the element must be equal to the heat flowing out of it, isn't it? Otherwise, there would be a net gain or loss of heat by the element and its temperature would not be steady. But in a steady state, the rate of heat flowing across a cross section of the rod is the same at every point along the length of the combined steel and copper. Okay, so let T be the temperature of the steel copper junction. This steel and copper junction, T is the temperature in the steady state. So then we can write K1 A1 300 minus T divided by L1 is equal to K2 A2 T minus 0 into L2, where 1 and 2 refer to the steel and copper respectively. And considering the data which is given in the question, so that is A1 is equal to 2 times of A2, L1 is 15 centimeter, L2 is 10 centimeter, and K1 is 50.2 joule per second per mole per Kelvin. Similarly, K2 is 385. So substituting all these values in the equation, we can write which gives the value of T is equal to if you simplify this, we get the value of T is equal to 44.4 degree Celsius. Okay. In the question also they have asked us to find out the temperature of the steel copper junction in the steady state of the system. So this is the temperature.